Hey, this is Mrs. Radigan with our last Chapter 2 lesson on solving inequalities. We are going to solve polynomial and rational inequalities. So any polynomial that has an inequality greater than or equal to, less than or equal to, or not equal to, we can solve. So if we want functions that are greater than 0, we're finding the values of x that make the function positive. Less than or equal to 0, we're finding those values of x that make the function negative. We are going to do that by using our sign patterns. So let's take a look at the first example here. We have a polynomial in factored form, so we can see that the zeros are at x equals we have x equals -3. This one, x squared plus 1, is going to give us imaginary zeros. So those will not affect our signs as they're positive. And then we have x equals 4 from the factor of x minus 4, and that one has a multiplicity of 2. So those would be our zeros for part A. If we're looking at part B, we need to use our sign patterns for finding when the function is positive. So we're going to go ahead and draw a number line with our zeros of -3 and 4 on it. And then we're going to look at those factors. So when we have a number less than 3 and we plug it in here, we get a negative. We're always going to get a positive when we plug it into this middle factor. And then when we have a number less than 3, we get a negative, but we always are going to square that, so we're always going to get a positive here. So that gives us a net negative output for our function. Right here, when we put in something between -3 and 4, this factor is going to change to a positive. The other two are always positive, so that means we're going to get a positive output there, and we're going to get the same positive output over here. If we look at the graph, we see we have our -3, 0, and our 4, 0 with multiplicity 2. It bounces there. And so we see that the function is negative down here and positive up here. So part B said positive, so if f of x is greater than 0, we would have not equal to, we would not include -3, but then we would go to 4. We would also not include 4 because that's equal to 0, and then we would go to infinity. If we include the zeros, then we would include -3, and we would include 4, so we just go all the way to infinity. If we want to know where the function is negative, so if it's just less than 0, it would just be negative infinity to -3, not including that. And then if we wanted to know where it was less than or equal to 0, we would have to include the -3, and we would have to include the value of 4. In this next example, we're going to use what we know about solving polynomials, about using P over Q, and then using our graph and our synthetic division to find all the zeros of the function. So we'll go ahead and find all the factors of 24 and put them over all the factors of 2. So we've got all our factors of 24 up here and all our factors of 2, and now we're going to make combinations like 1 over 1, 1 over 2, 2 over 1, 2 over 2, 3 over 1, 3 over 2, etc. So these are all our possible rational roots by making all those combinations. And if we look at the graph here on the calculator, we can see that we think there is a 0 at -2, at 4, and then maybe 1 there at -1/2. And we can verify that by using synthetic division with those roots. So we'll go ahead and verify the root of 4. We get a 0 here for a remainder, so that's a root. Then we'll try our -2, and we also get 0, so that means that 2x minus 3 is a factor that we get from our synthetic division, our root of x minus 4, and then our root of x equals -2, so x plus 2. So there's our 3 factors. And then we just need to use our sign patterns to determine when those values are positive and negative. So left of 2, we would get 3 negative values, which would make a negative. Between -2 and 3 halves, x minus 2 becomes positive, but these two are still negative. So we get a positive and 2 negatives, which makes a positive. Then one more, 2x minus 3 turns positive, so we have 2 positives and a negative, and then all 3 of them become positive. And if we look on our graph here, we can see that the function is positive between -2 and 3 halves, and then it becomes positive again here when x is greater than 4. So if we wanted to, in the original function, it said greater than 0, we would be in between -2 and 3 halves, and more than 4, but not including those values because those would make it equal to 0. So now we'll look at some special cases. If we have factors x squared plus 7 and 2x squared plus 1, we see that both of those factors give us imaginary roots. So that means that since this is an upward facing function, we are actually going to get no values on this function that are negative outputs. So if we were to define where the function is positive, we would actually get all real numbers. If we would define where it is greater than or equal to 0, we would also get all real numbers. And if we want to know where it was negative or less than, we would actually get no solution for both of these cases. This is a similar situation. This factor right here is going to give us 2 imaginary values. If you solve that with the quadratic formula, you're going to get x equals 3 plus or minus I root 3 over 2. So that gives us all imaginary solutions. And then 2x plus 5 squared is going to give us a root of -5 halves with multiplicity 2. That means that in one place we can get a function that's equal to 0, but we can never get a function that is less than 0. So for f of x less than 0, we have no solution. For f of x less than or equal to, we have just -5 halves. And then for f of x greater than 0, we have everything except -5 halves. And then f of x greater than or equal to 0, that would be any real number. Okay, in this next example, we have a rational function. It's written kind of funny here, but it should look like this. We're asked to find when it's 0. So remember, the zeros come from the numerator, if you remember from section 2.6 in the graphing. So we get x equals -1/2 as one of our solutions or x-intercepts. Our discontinuities come from the denominator, so we have x equals -3 and x equals 1. So in order to find out where the function is positive and negative, we're going to go ahead and make a sign chart with all of those values, -3, -1/2, and 1. And then so we plug in a number less than -3 and we get 3 negatives. we plug in a number between -3 and 1/2, and we get 1 positive and 2 negatives, which is going to give us a net positive. We plug in a number between -1/2 and 1, and we get everything but x minus 1 to be positive, so positive, positive, negative, so that gives us a negative. And then greater than 1, all 3 of these are going to be positive. So we would know that the function is positive between -3 and -1/2, and then greater than 1. If we want to know where it's just greater than, we would not include the -1/2 because that's the x-intercept that equals 0. If we want to know where it is equal to, we would include the -1/2. And then likewise for the negatives, if we want to know where the function is less than 0, we would go -∞ to -3 and -1/2 to 1. If we wanted to know where it's less than or equal to, we would just include the -1/2 because that is the root, but not the discontinuities of -3 and 1. Okay, if we have a rational inequality that has 2 fractions, we just need to put these fractions together by finding a common denominator, which would be x minus 1 and x minus 3. So we're going to multiply the first function by x minus 1 and the second factor or fraction by x plus 3. That gives us our common denominator. And then we're going to distribute and combine like terms. So I've distributed the 5 and the 3 combined like terms. Now I'm just going to factor out the 4 there. And I see all my factors. I can create the sign chart to find out where the function is positive and negative. So I include the x-intercept and the discontinuities. Again, just like the last one, these are the same numbers. And we get negative, positive, negative, positive. So it is less than 0 when x is between -∞ and -3, or -1/2 and 1, not including any of those values. If we look at this function with a radical, we know x has to be greater than or equal to -1, or we would have a negative under the radical. We also know we have a 0 at x equals 3, so we're going to put those values on a number line. We know anything left of there is undefined. If we plug in something in between here, we'd get a negative for the first factor and a positive, so that'd be a negative. And then anything bigger than 3 would give us 2 positives. So we know that our function is greater than or equal to 0 when we are greater than or equal to 3. And when this is a 0 also, so we need to also include the solution of 1, and we can see that on the graph there. If we look at a function that has an absolute value, we know our zeros are at -3 and 2 for this function. If we plug in something less than -3, we would get a negative over a positive, and that would give us a negative. Then we would get a negative over a positive again, so that would give us another negative, and then 2 positives, so that would give us a positive. So the function is less than or equal to 0 between -∞ and -3. We can't include -3 because it's a domain restriction for the denominator. So then we skip over that and we go on to 2, and we can include 2 because that makes it equal to 0. So in this problem, we're trying to design a box that makes at least 600 inches squared. We know we have a 25 by 20 and we're cutting out x, so we would get a function that looks like this. So we would set that function greater than or equal to 600. We would graph the function on one y equals and 600 on another, and we want to see where it's greater. We see that's between 1.6 and 6.19, so